Hello, everybody, and welcome to the virtual seminar series on Bayesian decision making and uncertainty. We're really excited to have everybody here. Thank you for joining us. My name is Alex Turenin. I'm with Cornell and one of the organizers who's going to be hosting today's event. I'd like to thank my fellow organizers, Renato Berlinghieri, Natalie Mouse, and Z Wang for their work in helping put the series together. And before we get started, I'd just like to make a few organizational announcements. The first of those is we're going to be taking a short break after this seminar for a couple of weeks, but in a not so long amount of time, let me say what the date is. Starting on the 5th of May, we're going to have more speakers lined up. And so check that out. You can find this schedule on our website. It's gp-seminar-series.github.io. And yeah, you can sign up there if you're watching on YouTube and interested in registering. And yeah, check it out. And you can always join the seminars either via Zoom, as long as you register in advance, on our website. There's a Google group that you can sign up to, and then we email links through that. Or you can always watch us via YouTube, which does not require any registration. The typical time for seminars is 1600 UTC, which is Universal Coordinated Time, and always be mindful of how your daylight savings time may change that. Uh, for today's seminar, if you're joining us via Zoom, you can ask questions by typing them into the chat, and the speaker can sort of, choose to pause and answer questions, or can hold them in the end. It depends on their preferences. And with all of these announcements said, it's my great pleasure to introduce Qian Xi, who is a PhD student at Cornell and will give today's seminar. Qian, the floor is yours.
Hey Alex, so let me turn on my video and start sharing my screen. It works, right?
Yes.
Okay. So hi everyone. Thanks Alex for inviting me to give a talk at this wonderful seminar series. Today, I'm going to introduce about my recent work on cost-aware Bayesian optimization via the Pandora's box Gittins index, which is a work bridging between two areas, Bayesian optimization in machine learning and Pandora's box Gittins index from economics and CS theory. So these are my wonderful co-authors, including my advisor, Ziv, the organizer of this seminar series, Alex, Peter, the first speaker of this seminar series, and Raul. So first, I want to give some background about Bayesian optimization. So we are living in a world of hyperparameter optimization. Say, for example, when we when we do hyperparameter tuning for machine learning model training, we might have hyperparameters such as learning rate, number of layers, batch size, to achieve higher accuracy. Another example is when we do control reinforcement learning. Say, for example, this lunar lander problem in OpenAI Gym. So we might have control variables such as positions, velocity, angles, in order to achieve high rewards. Say, for example, we may want this lunar lander to safely land in our target area. A third example is adaptive experimentation in online economies. So we might have, say, we may want to do some A/B testing to find out a good version that achieves high revenues. And we are also not limited to just say discrete versions like A version versus B version. These decision variables can also be continuous. So what are in common for this hyperparameter optimization? So our target function may not be analytical, and there might be no gradient for us to easily do the optimization. So we treat such problem as black box optimization, where we have some input hyperparameters and then some black box processes would output a performance metric that we want to optimize. And we can model it as a black box function drawn from stochastic process to address this uncertainty. So traditional approaches include grid search and random search. However, these methods might be very, time consuming. So are there any more efficient approaches that is more adaptive, more data-driven? Because I mentioned, there was one thing I forgot to mention, that is the problems we are interested also has a property that these black box functions might be expensive to evaluate. And we also have limited number of evaluations. That's why we want more efficient approaches compared to grid search and random search. And Bayesian optimization is exactly the approach that is more adaptive and more data-driven. The key idea is to maintain a belief about this black box function using something called Gaussian process. Because Gaussian process has very good properties that we can apply the Bayesian rule, and then say, for example, we start with some prior. In this example, we have a zero mean and unit variance. And then after we collect some observations, we can update our belief by applying the Bayesian rule. So now you will see we have almost zero uncertainty at these observations. And then we have higher uncertainty at the points that are far away from these observations. So this blue line is the mean, is the posterior mean, which represents the prediction. So then we can make our decisions about what to query next based on such prediction and uncertainty information. So is there any optimal policy that guides our decisions of what to evaluate next? Unfortunately, we might have a continuous search domain which means that we might have infinite number of choices. In some other cases, we might have discrete search domain, but the number of choices might still be very large. And then also, these values can be correlated. So closer points might have more closer values. And then such correlations also make this problem harder to solve it exactly. So correlation and continuity will lead to an intractable Markov decision process, and thus the optimal policy remains unknown. So given this, people propose some heuristics for solving this problem. The most popular one is called expected improvement. The idea is that, now we have, for example, we have 4 data, and then this is the best observed one. And then for each point in the search domain, based on this posterior mean and variance, we will see if what is the probability it will be above or below this best observation, and then we compute its so-called expected improvement over this best observed value. So we can view this expected improvement policy as an one-step approximation to the Markov decision process. And it would give this acquisition function, which we can optimize it to find out the point we want to evaluate next. There are also other improvement-based policies, such as probability of improvement, knowledge gradient, multi-step look-ahead expected improvement. So this multi-step look-ahead EI can be viewed as a multi-step approximation to the MDP, which is, also starting from how to approximate that MDP, that intractable MDP. There are also some other approaches based on other principles. For example, entropy-based policies, such as max value entropy search and predictive entropy search. There are also upper confidence bound and Thompson sampling. Each of these approaches has its own principle. So given so many approaches, we propose another approach called Gittins index. And you might wonder why another approach? So the first reason is that our approach can achieve competitive empirical performance. So here is an overview of our experiment results. We test our Gittins index policy and compare it versus many baselines that I just mentioned on both synthetic experiments and empirical experiments. So this green line is our Gittins index policy, and you can see it achieves competitive performance with some state-of-the-art policies, such as Meta's recent work on the log variant of expected improvement called log EI, which is the blue line. Oh, the order was a little bit wrong. This should go first. So these are the objective functions of the experiments I just mentioned. I will return back to our experiment results later. So I just talked about competitive empirical performance on traditional Bayesian optimization. The next reason is that our approach is also applicable to richer variants. For example, varying evaluation costs. So in fact, varying evaluation costs can be in almost every real-world situation. One example is that the runtime can be different across the search space. So say in machine learning model training, different number of parameters might lead to different runtime. It will have more layers and higher batch size, then you will have more model parameters, and thus the runtime might be higher. And then also in this lunar lander control example, the landing time can also be different. Also, when you run adaptive experimentation, testing different variants can also have different time or consume different resources. So if we can address such very evaluation costs, that will help us make the decisions better. So besides modeling the target function, we can introduce another cost function for varying evaluation costs. And we call this problem cost-aware Bayesian optimization. Oh, it was proposed by a prior work, which is exactly titled cost-aware Bayesian optimization. And then it was also formulated in this work, multi-step budgeted Bayesian optimization with unknown evaluation costs. So our goal is to maximize the target function such that the total evaluation cost is within a given budget B. So our work also extends to expected budget constraint, where the total evaluation costs can be within the budget in expectation. I will also return back to this point later. So how do people approach cost-aware Bayesian optimization? They start from the policies for the uniform cost case, and then see how we can adapt it for varying costs. So say we have expected improvement I just mentioned. Then there's work expected improvement per cost, which considers dividing the expected improvement acquisition function over the cost function. and pick the maximum one as the point to evaluate next. So then why divide? This decision sounds a bit arbitrary. And also, there was prior work analyzing about this policy, and then found it can be arbitrarily bad in some very bad instances. Then there are also multi-step approaches based on multi-step look-ahead EI. The cost-aware variant is called budgeted multi-step look-ahead EI. However, the multi-step approaches can be a bit slow. It's also unclear about the cost-aware variance of upper confidence bound and Thompson sampling. So in our view, these approaches lack of a guidance to incorporate costs. And our new design principle, Gittins index, is inherently cost-aware, which is well suited for this cost-aware Bayesian optimization problem. So how we get the idea of applying the Gittins index to cost-aware Bayesian optimization? We start from its two properties, the continuity and correlation, and then think about, oh, what are the corresponding discrete and independent version? And then we find, oh, this seems to be very similar to a problem called Pandora's box problem, which was proposed by Weizmann early in 1979. So there was about for more than 40 years ago. And this problem, as its name suggests, is as follows. So you have a line of boxes which has some hidden rewards inside. You can observe its distribution, though you have no idea what is the exact value inside. You can pay some cost to open some of the boxes and see the reward inside. Then you pick one of the best box after you open some boxes. So here is the decision-making process. So at the beginning, we start with closed boxes and their distributions. And then we pay a cost to open a box, pay another cost to open another box and see the values inside. And then open some boxes. Okay, this one has the highest reward. We decide to stop and select this box. And the target and our objective is to design a policy that can optimize the expectation of our reward, subtracting the total cost we have spent. Then by comparing comparing the formulation, there is also a subtle difference That is, in cost-aware Bayesian optimization, we have a budget constraint. And in Pandora's box problem, we have an unconstrained optimization. So there's also a difference between these two types of problems. That is, one is expected budget constraint, and the other is cost, what we call it cost per sample. So this Pandora's box policy has an optimal policy, a Bayesian optimal policy, Gittins index. So what is Gittins index? The high level idea is that we assign each box a Gittins index. For maximization problem, higher the Gittins index, better the box is, we think. And for the minimization problem, lower the Gittins index, better it is. So for closed box, we use the distribution information and the cost information to compute a Gittins index. And for an open box, the Gittins index is exactly the value reviewed. And then we open the box with the highest index. So say, for example, this box has higher index than this box, then we open this box if it is closed. If the open box happens to have if an open box happens to have highest index, then we select it and stop. So this is the idea of Gittins index policy. Then how do we translate this Gittins index policy to cost-aware Bayesian optimization? Given these differences in the problems, so the first step I want to talk about is the conversion between cost per sample and expected budget constraint. So starting from Pandora's box, if we convert it from an unconstrained problem, if we connect this unconstrained problem with the expected budget constraint problem, which we call it budgeted Pandora's box, that is given a budget, and then the cost we have paid to open these boxes are within this budgeting expectation, and then we want to maximize the value we have found. So there's a concurrent work called Markovian search with socially aware constraints, which happens to study the same budgeted Pandora's box problem, though their name doesn't have Pandora's box in it. So both our ideas are to apply Lagrangian relaxation between these two problems, which would introduce a Lagrangian multiplier before our cumulative costs associated with our budget, which can also be viewed as a scaling factor to the cost. Because in the Pandora's box problem, since it's a theoretical problem, it does not consider the practical aspect of this course. That is, they can be in different units with our objective. Our objective might be, say, cross-entropy accuracy, while these costs are runtime, or they can be, in dollars, in RMB. So and they can also be very large or very small. So this Lagrangian multiplier can be viewed as a scaling factor for these costs to account for the trade-off between our objective and cumulative costs. Then our conclusion is that there exists an optimal policy for this budgeted Pandora's box by solving the equivalent unconstrained version of this cost per sample objective with this Lagrangian multiplier scaled for the costs. And the Gittins index policy for that problem is an optimal policy for budgeted Pandora's box. So our work extends this concurrent work to from discrete reward distribution to general reward distribution, because since we have Gaussian process, which will give us non-discrete reward distribution. So this is also a theory part of our work. So I just talk about the relationship between expected budget constraint and cost per sample. And then the next thing is how do we translate Gittins interface policy by addressing the difference between continuity and correlation. So starting with this Gittins index policy with scaling factor involved, we just incorporate the posterior given by the Gaussian process, and then just use this posterior distribution to compute Gittins index at every iteration as our acquisition function. So now we have our Gittins index acquisition function. Then you might wonder, how do we compute Gittins index? So let me return back to the Pandora's box problem I mentioned. How do we use the distribution information and the cost information to compute Gittins index? The idea is that we consider this so-called 1.5 box problem, which is a simple problem reflecting our exploration trade-off, whether to open a new box or take current best. So we can write out the profits of opening a closed box versus taking an open box. So taking an open box, the profit is simple. That is exactly what it has the value inside. And then for opening a closed box, there will be two cases. One case is that when you open it, you found the value is better than the opened box. So you will prefer to take this value. And if you found it is below the revealed value, then you will just give up and then still take the open box. So here is the expected profit. You also want to subtract the cost here. Then by comparing these two expressions, you can have a solution that makes you indifferent between these two choices. And this solution is exactly the Gittins index. And then you would also find out that larger the cost, smaller the Gittins index, based on this expression, which matches with our intuition. If we rearrange this expression, then we will have the cost as one side, and then this expected improvement on the other side. So I would return back to the connection between Gittins and EI later. So then it's naturally to ask, Gittins index is optimal for Pandora's box problem. Is our adapted Gittins index acquisition function good for cost-aware Bayesian optimization? So in this work, we show that it is empirically good. So these are the objective functions that I just mentioned. They include both synthetic objective functions and also practical objective functions. And we also conduct experiments in both the uniform cost case, that is, we treat every iteration to be uniform, and also varying costs case where querying different point would have different evaluation cost. So again, the green curves are Gittins indices. And then we can see that it is competitive uh, in these scenarios. And then most of the time it is the best one. And you can also find out that the second best policy is not always always the same. So sometimes log EI can be as competitive as Gittins index, but sometimes it is not that competitive. In terms of the question whether Gittins index acquisition function is theoretically good, and we are still studying about this problem. And hopefully we can get something out. Okay, I just mentioned that I would return back to the connection between EI and Gittins index. So first, here I show the counter plots about EI and Gittins index with different cost scaling factor lambda. So you can see that when Gittins index has the larger lambda, then the counterplot seems to be more similar to EI, though not exactly the same. Well, when Gittins index has smaller lambda, then such counterplot seems to present a pattern that is linear in standard deviation and mean. So it's more similar to UCB, the upper confidence bound. Later, I would also return back to the effect of a large lambda versus a small lambda. But for now, I want to continue talking about connection between EI and Gittins index. So you can see that EI acquisition function actually appears in the expression of Gittins index function. It's just Gittins index is solving the equation such that the expected improvement of our solution equals to the scaled costs. And what does this imply? So we know that our posterior distribution is a Gaussian distribution, so that we have an analytical expression for the EI acquisition function. Then Gittins index acquisition function is easy to compute using EI acquisition function and bisection search or other optimization methods for solving the solution of this expression. So we have also conducted timing experiments by comparing Gittins index with baselines. And then one can see it is, though it's not as fast as EI and Thompson sampling, but it's super close. And compared to its difference between its difference in time between Gittins index and other slower methods such as multi-step look-ahead EI and knowledge gradient. I also just mentioned the effect of lambda, the cost scaling factor. So from this plot, you can see that with a larger lambda, then you have a faster decreasing rate in the regret, but it also flattens earlier. While with the smaller lambda, you have a slower decay rate in the regret, but also it can achieve lower regret later on. So this implies that if we have a larger budget, then we can pick a smaller lambda, which reflects higher exploration. If you have a lower budget, then you can pick a larger lambda and exploit more. One can also consider a schedule of lambda. So we also proposed PBGI with decay lambda in our paper. You can also check out the experiment results of it. So so PBGI with a decay lambda, the advantage is that if you have no idea of how whether your budget is large or small, then it will be a good choice. And then it is also consistent. That is, eventually it can, if you have infinite budget, you can find the global optimum. Okay, so in summary, we propose a new design principle called Gittins index for cost-aware Bayesian optimization. the key idea is that we link to another problem from economics and theoretical computer science called Pandora's box, which um, has a framework, Gittins index theory, that shows some optimality. Uh, and we have conducted experiments to show it has competitive empirical performance. And this work opens a direction about combining Bayesian optimization with Gittins indices, particularly for cost-aware and stopping-aware problems, given the properties of uh, Pandora's box and Gittins indices, which are inherently cost-aware and stopping-aware. Thanks for everyone, and I welcome questions.
So I wanted to start by thanking Qian for the talk. And there's going to be two stages of questions that people can ask. The first of those will be streamed to YouTube. And then afterwards, there's going to be another phase of questions that, in case anybody doesn't want to ask their question live.
Sounds
So we can move to the first stage. And I guess in the absence of any questions, I'm going to go ahead and conclude the live stream. And before I do so, I just want to thank all of our listeners on YouTube for joining us and remind everybody that we have another seminar coming up in a couple of weeks. And you can always find the schedule on our website, which is gp-seminar-series.github.io. And thanks for joining us today. And please feel free to join us next week. Thank you so much. Or rather,